Welcome back, Professor C.N.R. Rao, who's been a friend for many years, to give a wind-distinguished lecture here in our Quantum Nano Center. When Professor Rao, who's a member of our International Scientific Advisory Board, was here last in 2010, only the framework of the QNC building could be seen, of course, and the Nobel Prize in Physics for work on graphene had not yet been announced. His lecture highlighted some of the distinctive properties of graphene, and today he will talk about graphene analogues and related materials. Professor Rao is National Research Professor as well as Honorary President and Linus Professor at the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore, India. He is also Honorary Professor at the Indian Institute of Science. Both of those institutions are shown on the slide there. He is one of the world's foremost solid-state chemists and material scientists. Professor Rao has an incredible publication record. He's the author of over 1,400 research papers and 45 books. He received his MSc degree from Banaras Hindu University and a PhD from Purdue University, and he has, believe it or not, received 60 honorary doctorates from around the world. He's also a member of many of the major science academies of the world, including the Royal Society of London, National Academy of Sciences, the USA, the Russian Academy of Sciences, the French Academy of Sciences, the Japan Academy, as well as the American Philosophical Society. He's also a fellow of the Royal Society of Canada. He serves on the editorial boards of several leading professional journals and is a distinguished visiting professor at the University of California and Cambridge University. Now, he's obviously won a very large number of awards and medals over more than 4 decades, so they're far too numerous to list. But let me just mention a few of the notable ones he has received since 2000. He was awarded the Centenary Medal of the Royal Society of Chemistry in 2000 and the Hughes Medal of the Royal Society of London for original discovery in the physical sciences the same year. Professor Rao was honored by the President of Brazil in 2002, receiving the Order of Scientific Merit, that is the Grand Cross. He was also the first recipient of the India Science Award. He was named a chemical pioneer by the American Institute of Chemists in 2005. The same year, he was presented with the Chevalier de la Légion d'Honneur by the President of the French Republic. The Nikkei Asia Prize for Science, Technology and Innovation was awarded to him in 2008. The Royal Medal of the Royal Society in 2009, and the August Wilhelm von Hoffmann Medal of the German Chemical Society in 2010. Finally, he won the Ernesto Illy Trias Science Prize for Materials Research in 2011. He was Albert Einstein Professor of the Chinese Academy of Sciences in 2012. It's an incredible record. Professor Rao is Chairman of the Scientific Advisory Council to the Prime Minister of India and member of the Atomic Energy Commission of India. So please welcome Professor C.N.R. Rao, who's going to talk about inorganic graphene analogues. Ram?
Yeah, thank you. So thank you. This is working now? Oh, okay, fine. Good afternoon. I'm very happy to be here on this occasion, also giving a talk on something that we have been doing in the last 3 to 4 years after graphene became famous. We started looking at graphene analogues. I'll be mainly talking about that. And more than that, in the last 1 year, some of the work I started 5 years ago has received a different kind of importance. Suddenly, materials of importance in the world today are materials which are related to these layered materials. One of the most famous examples being molybdenum sulfide. I'll mention that, why it is so. A lot of work going on in MOS2. In fact, I started on this single layer MOS2 about 4 or 5 years ago. But it's really nice to see this entire area taking a different form and shape because of innumerable applications, particularly in producing hydrogen by water splitting and making unusual electrodes in batteries, a whole bunch of applications that some of these materials have found in the last 2 to 3 years. I will not be talking about all those applications, but I will refer to some of them anyway during this talk. Well, I talked last time about graphene. I will take the first 5 minutes to put you in the right frame talking about graphene. Graphene is a well-known two-dimensional sheet of sp2 carbon atoms. It is the mother of all graphitic forms because you can stack them and make graphite, roll them, make nanotubes. You can even make buckyballs out of graphene. The reason graphene became important and the Nobel Prize was given is for this one frame because of the extraordinary electronic behavior. It has ballistic transport of electrons. The energy of the electrons is linearly dependent on the wave vector near the crossing points of the Brillouin zone, these K points. And this is a zero gap material. There is a disadvantage actually for applications. You need a small gap to have for many applications, but of course there are ways of inducing the gap in graphene. There are many interesting properties, particularly this electronic structure and properties of graphene is what made it famous. That's what gave a very quick Nobel Prize because of this reason. And now, how does one make it? What these people did was to take a graphene crystal and put a Scotch tape and peel off the top layer and get one graphene layer. In fact, this is nothing new. People have tried to do that 50, 60 years ago, but there was no way they could characterize what they got at that time. And today, of course, we know what you get when you peel off a layer with a Scotch tape. And you see, you can do that, and you can get a single or bilayer graphene, and you can measure the heights of these or thickness of these things and know whether you have one layer or two layer by micromechanical cleavage. But normally, however, most people don't do this, prepare graphene by this. They use chemistry. That is why I've just briefly mentioned this chemistry. Most people, what they do is take graphite, oxidize it, exfoliate graphite oxide, get single layer graphene oxide, then reduce it and get some sort of a graphene. It is actually reduced graphene oxide. You can make single layers of that in solution. And one of the methods we originated in Bangalore was by arc discharge in the helium-hydrogen atmosphere. You can also get sort of a graphene sample. There are many articles, reviews. In fact, I myself have written many of these articles in the last 3-4 years. And I'm not going to belabor the point that graphene can be made in various ways. And one of the nice ways, even physicists can use this method, is by making single layer graphene oxide in solution, yellow solution. Just put it in sunlight. If you don't have to do sunlight, you have UV light or laser irradiation. Slowly, that yellow solution becomes black. You have a nice graphene dispersed in solution and dispersed in a solvent. And you can see by looking at the infrared spectrum how all the oxygen functionalities in graphene oxide disappear as you irradiate with laser radiation or ultraviolet light. So these are all the methods, and there are a number of methods. I'm not going to talk about that, just to show that today we can make graphene in different forms by a number of methods, particularly by CVD and metal surfaces, a number of other methods. So I just want to show that we have now made it. Not only that, we can also make graphene which is doped with boron or nitrogen. In fact, this is an old paper of mine, 3-4 years old, where we were the first to actually dope graphene with boron or nitrogen. And of course, the right away when you dope it, you introduce a gap. You get a small gap, and you get semiconducting graphene, and with a little gap, and with N-doped or boron-doped, you have P-type or N-type of graphene, and you can do that as well. So these are all some of the things that were done. And one also made important things like materials like graphene nanoribbons. If you take graphene, which is a sheet, you cut it into a rectangular piece, it becomes a ribbon. And this ribbon, you see, one way of making it is by oxidizing carbon nanotubes. Of course, the method we used is to use a laser, unzip, you see the nanotube, unzip it and make a strip. And this is a very nice way of making very clean nanoribbons. And all this has happened in the last few years. More than that, a number of properties. Again, I'm telling you all this because this kind of a background may be useful for the talk I'm going to give on the analogues of graphene. Graphene, you can make a transistor out of it, field effect transistor. You can dope electrons and or holes in it by electrochemical means. The same thing you can also do by putting a molecule on it. If you take graphene and put on its surface an electron donating molecule like tetrathiafulvalene, or you can put an electron withdrawing molecule like a tetracyanoethylene, you can see the shifts in the Raman band. The Raman G band shifts to higher frequency, higher frequencies when you withdraw electrons, lower frequencies when you donate electrons, showing thereby it is highly sensitive to p-type and n-type doping, even by molecular interaction, molecular charge transfer. So it is very similar to n-type, p-type doping you can do electrochemically. So these effects on graphene are very, very significant, very interesting. For example, you can see when I put tetracyanoethylene, the shift of the Raman G band with the tangential mode is extraordinarily large, nearly 20 cm-1, which is a very large shift as you go on doping, putting molecules like TCNE on the surface of graphene. You can also do the opposite, withdraw electrons and change the position of this band. So these are all some of the interesting properties of graphene. And there are also many other properties, like for example, graphene is a big fluorescence quencher. You have any molecule which gives fluorescence, you put a little of graphene, it quenches the fluorescence, and you can study why it does so. And these are all unusual characteristics of graphene. And it also has a magnetic properties. For example, if you take a piece of graphene, it is weakly magnetic, even at room temperature. You can see ferromagnetic hysteresis. So this solves the old problem. But 50 years ago, there were papers from MIT, for example, is graphene or graphite magnetic or not? Graphene certainly is magnetic when you make small bits of it in graphene nanoribbon forms and so on. And we do see magnetic hysteresis at even room temperature because of this reason. I just am giving you a summary of some of the properties of graphene, and I'll skip this. You can even make wonderful field emission devices using graphene, just like with nanotubes. Many of you know carbon nanotubes are being used already for flatbed displays. I feel that the low turn-on field emission and so on we find in doped graphene or graphene makes me feel that they may be very well used for making flatbed displays and so on. Okay, well, this is one of the things that we did some time ago. You see graphene, slightly you put some surface impurities. Graphene immediately has a small gap. That gap is somewhat comparable to the energy of infrared radiation. So therefore, if you use this graphene material, it becomes a highly heat sensor, infrared sensor. You can see the infrared light when you put a radiation infrared laser, if you put it, you can see wonderful signals. In fact, I have shown here, when you just put your hand in front of this graphene detector, you can see the presence of the hand, or when they remove the hand, you can see the signal. Very, very sensitive infrared detector is what you can make with graphene. So these are all the properties. The last one I want to mention is the mechanical properties of graphene. You can put graphene in a polymer, and it strengthens the polymer both in terms of the modulus and the hardness. And in fact, what is more interesting is this work we published in the Proceeding National Academy of Sciences about 3-4 years ago. When you take graphene and put a small amount of another nanocarbon like a nanotube or a nanodiamond, 0.1, 0.2%, there is enormous synergy in mechanical properties, and this can be exploited even practical purposes. So these are all some of the things I have mentioned just to remind you that graphene is a very interesting material, very exciting properties. That's why people have worked on it. Today I'm not going to talk about that, but analogues of graphene. What do you mean by analogues? There is enormous literature, inorganic compounds which are layered. Well-known layered material is boron nitride, exactly like graphite with 6-membered rings, you got boron nitride. Another layered material is molybdenum sulfide. It doesn't have this kind of 6-membered rings, but it is also a layered material. So we have all these wonderful materials which are layered. So why not do something with them? Well, for those who remember, when fullerenes were made. Fullerene was first made in the laboratory in 1990. It was discovered in 1985 by dear friend Harry Croto and also Smalley, but it was made in the lab in 1990. Immediately people said, why not make inorganic fullerenes? You see, niobium sulfide, tungsten sulfide, these are all layered sulfides, and we can make fullerenes of that. This was done by my very good friend Rashef Tenne in Weizmann Institute, and this is the fullerene structure made by us in Bangalore. Very nice fullerene type structures can be made by layered inorganics, just like in the case of carbon materials. So we call them inorganic fullerenes. The same thing was done when nanotubes were discovered. Carbon nanotube was fully discovered or fully described only in 1991. For those who may not know, it's very interesting history, nanotubes. It was made first time in 1976 by a friend of mine in Japan, but nobody noticed it. But it's only when Iijima made it in 1991 and described it, everyone credits Iijima with the discovery, but actually it is very unfair. It had been done earlier. Doesn't matter. These carbon nanotubes, when they were made, immediately we could make nanotubes of various kinds, particularly of the layered disulfides, selenides, and I'm just showing you the one on sulfides and selenides. This is the molybdenum sulfide nanotube. Similarly, many other nanotubes. Boron Nitride nanotube is very easily made. So this all is a background. So why not make graphene-like material with inorganics? So one can make it just like graphene was made by taking a molybdenum sulfide crystal, using a scotch tape, peeling it off, or you can also make by a number of chemical methods, by lithium intercalation, exfoliation, hydrothermal methods, a number of various techniques, chemical methods are available in fact. Well, how do you know you have made it? Well, you see there is a 002 reflection in the X-ray diffraction, and that immediately disappears as soon as you make a single layer or a two-layer molybdenum sulfide. And then you can also study the electronic structure. This is a calculated structure. Bulk MOS2 has an indirect band gap semiconductor, and now as soon as you make a single layer, it becomes a direct band gap semiconductor with a band gap of 1.7 eV. So these are all some of the interesting things that were done a few years ago, 3-4 years ago, and many other things. We can also do very high resolution electron microscopy. Unfortunately, some focusing problem is here. But anyway, you can see every atom of molybdenum sulfur. You can photograph these very nice single layer or two-layer molybdenum sulfide. I'll show better pictures in a minute. There are some defects which I'll not be discussing today. Well, here is another picture of tungsten sulfide. You can see all the atoms very clearly. You can see this is a low resolution picture showing 2 layers and 3 layers of tungsten sulfide. Just like graphene, there are layered materials forming graphene-like. Instead of 2-layer graphene or 3-layer graphene, we have 2-layer tungsten sulfide or 3-layer tungsten sulfide or a single-layer tungsten sulfide. So these are all things which we made. And here is a bunch of very nice pictures. Here is molybdenum selenide and tungsten selenide. You can see in molybdenum selenide that single layer is there. In this region, there are 2 layers. You can actually do a transformation and see what is what. We can analyze these electron microscope pictures very nicely. Here is a tungsten selenide, a single layer tungsten selenide, a high resolution microscope picture of that. So we can study all this microscopy, structure, and a number of properties of this single or 2-layer sulfide, just like we did in the case of graphene, and that has been done. In fact, you can make these materials by a number of other methods. For example, you can make by laser exfoliation. You can also make by microwave synthesis, a number of methods which I will not talk too much about now. But one of the important things is Raman spectroscopy. Because being Indian, I'm so happy that Raman spectroscopy has become so powerful. Raman spectroscopy is the only way you can study most of nanocarbons, nanotubes, for example. Without Raman spectroscopy, you cannot really understand nanotubes. Same with graphene. The only spectroscopic signature you have of graphene is through Raman spectroscopy. So Raman spectroscopy is also very useful in molybdenum sulfide. For example, these are some of the vibration modes of molybdenum sulfide. But let us take 2 of them, the A1G and the E1G, these 2 modes. If you see, the Raman spectrum of bulk molybdenum sulfide is like that. If I make one layer, this band shifts, goes to the left, that is, it softens, and the second band goes to the right, it stiffens. So the softening of the A1G mode and the stiffening of the E12G mode as you vary the number of layers. You see, from bulk, you come down to one layer, you see the softening, decrease in frequency, E12G increase in frequency. This is very, very useful in characterizing single, two, triple, double layer molybdenum sulfide and materials of this kind. And it is also a very interesting spectroscopy actually by itself. Molybdenum sulfide also gives magnetic properties just like graphene, because of these also have edges and so on. You see, for example, if you take this is a nice molybdenum sulfide electron microscope picture, you see these edges with just like graphene, which has lone pair orbitals. We have zigzag edges with unsatisfied valences, which partly contribute to the magnetism of these nanosheets of molybdenum sulfide, selenide. We also have various kinds of defects which are of interest, but today I will not go into too many details of this because I want to cover the topic in some way. Now, this is one of the things I just want to mention. If you remember, I started my lecture saying, when you take graphene, you can dope holes and electrons. That is, you can dope holes also by molecules, by withdrawing molecules by using tetracyanoethylene. Or you can dope electrons by putting tetrathiafulvalene. Well, we tried to do the same thing with molybdenum sulfide. Here is a surprise. You see, tetracyanoethylene, when they try to put tetracyanoethylene, if it withdraws electrons, it had no interaction with MOS2. The reason is MOS2 is a p-type semiconductor, and you can, because of that, only you can donate electrons, but you cannot donate holes. However, if you try to donate electrons by putting a molecule like tetrathiafulvalene, in fact, as soon as you put a molecule, what happens is the molecule itself transforms. The tetrathiafulvalene becomes a radical cation. It transfers an entire electron to molybdenum sulfide sheet. Of course, the same things we have done also by using a transistor and then doping electrochemically. Then we find only electrons can be doped into tetrathiafulvalene, but no holes because it is a p-type material. Of course, what is interesting is the minute I dope electrons by using this molecule, the molybdenum sulfide becomes somewhat more like a metallic system. It was before it had if you remember, it was an indirect back semiconductor with a 1.6 electron volt gap. But when you put these molecules, you get a metallic surface. So you can do very interesting transformations of the surface of these layers by just putting a molecule on the surface. So this has a lot of future in many applications, but I will not be able to talk about it today because there is a lot of research yet to be done on exactly how to exploit the nature of changes in the electronic structure of surfaces of these layered compounds by putting molecules of this kind. Well, we can also do reactions. For example, molybdenum sulfide is involved in a very famous reaction, namely hydrodesulfurization catalysis, MOS2. That is very important in petrochemical industry, where you want to get rid of thiophene. It converts to butane in a hydrodesulfurization. We have done that with a single layer or two-layer MOS2 by itself, or by putting a few nanoparticles of nickel or cobalt. By doing that, we actually find, what is that? Okay. We actually find tremendous improvement. These sheets of molybdenum sulfide, nanosheets with these nanoparticles, really do hydrodesulfurization very effectively. Even starting at a very low temperature, you almost get 100% desulfurization by around 400 degrees. So these are all some of the interesting chemistry with associated with I don't know why it is not shifting. All right. All right. Well, what we have done now is, in the last year or two, is to actually make transistors out of these. This is a field effect transistor made out of molybdenum sulfide. And you can see, take these layers and make a nice transistor. And of course, you can see how many layers you have put by using the Raman spectroscopy, looking at the A1G band and the E1-2G band. You can see, as I told you, the A1G band softens, E1-2G band stiffens as you decrease the number of layers. So you use a single layer or a two-layer MOSIS2. You know what you have done by doing atomic force microscopy. You can see the thickness of this layer is exactly 0.7 nanometers. That means it's a single layer molybdenum sulfide I've used there. And then you can do properties, transistor properties of this material. Okay.
This is the advanced button.
Yeah, okay. Okay. Oh, I'm sorry. So we have studied the transistor properties, some particularly to understanding some hysteresis and phenomena of this kind. So we now are making devices using inorganic layered materials. There are many possible applications for these devices using MOS2. You can also make an IR detector, either in transistor configuration or otherwise. You can see, just like graphene, molybdenum selenide, which has a small gap, smaller gap than molybdenum sulfide, is a very good infrared detector. So we have been able to do that as well. And then one of my colleagues has used them in lithium-ion batteries. I'm sorry, these are wrong references in some other journal. Lithium-ion batteries, very, very good performance using molybdenum sulfide as the electrode material, or tungsten sulfide. Tungsten sulfide is slightly better. Along with graphene, if you use it, it gives very good performance as an electrode in lithium-ion batteries. Now, these are all some of the things. I would like to spend 2 minutes on the next few frames, because this is something very interesting. It is just coming out this month in Angewandte Chemie, and I would like to talk about that. You all know about photosynthesis. In photosynthesis, what leaves do is take water and split the water into hydrogen and oxygen. In photosystem 2, water goes, and there's the inorganic oxygen, calcium, manganese oxygen unit, which breaks up the water into oxygen and hydrogen. Oxygen comes out, hydrogen goes and eventually makes food in some way. Of course, it goes to photosystem 1 and so on. I'm not bothering with that. So one way of doing splitting of water is by catalysis using various kinds of nanoparticles. Recently, we have succeeded very nicely by using oxide nanoparticles, particularly of cobalt and manganese, which have, these oxides must have cobalt and manganese in a particular oxidation state and spin state, very important. They must all have a 1 electron in the EG orbital. That is what we have shown. And that splits water beautifully. And that paper of mine has just come a few weeks ago in Proceedings in the National Academy of Science. But that is one way of oxidizing water to get oxygen and so on. To produce hydrogen, you can use various kinds of semiconductors where you excite the electron, and that electron is used in some way eventually to reduce the protons that are produced by water splitting. And then you get hydrogen. And there is a lot of work in the last 1 or 2 years by people to use molybdenum sulfide for producing hydrogen. What they do is make a composite of molybdenum sulfide with graphene. And so we also thought we will do that. We took molybdenum sulfide and made a composite with reduced graphene oxide. You see, the amount of hydrogen given is not very high. So we thought, well, you know, after all, what is happening is graphene is acting as the electron channel for molybdenum sulfide. In this gives electrons. You see, the protons go on molybdenum sulfide surface. The electron comes through graphene, and those electrons reduce the proton into hydrogen. That's what actually happens. So if that is the case, I must have a better electron channel. So what we did was, instead of using simple reduced graphene oxide, we highly hydrogenated, nitrogenated it. Well, as much as 15% of nitrogen we could dope in reduced graphene oxide. Immediately, you see, we got very, very excellent performance in hydrogen. So what was giving 0.05 millimoles per gram per hour is suddenly became 3 in the case of reduced graphene oxide. But the minute I put nitrogenation, it became 10.8 just with a 100-watt lamp, or 42 millimoles per gram per hour, a very, very high hydrogen evolution with a very high turnover factor. We got that. Well, this gave us, in other words, highly nitrogenated reduced graphene oxide is a good way to produce hydrogen using molybdenum sulfide as the surface for reduction of protons. Well, if this is the case, why not I do something with molybdenum oxide itself? Forget about this graphene. Why do I need graphene? So in this process, what we did was make a new kind of molybdenum oxide. You know, this is where chemistry and material science, somewhere in the back of my head I knew if I did some alkali metal intercalation in molybdenum sulfide and exfoliate it in some way, you get a new form of molybdenum sulfide. Ordinary molybdenum sulfide is 2H polytype. But if you do by this exfoliation of lithium, you get a 1T polytype. 1T polytype is highly conducting, it is metallic. It is not like 2H polytype, which is the indirect band gap semiconductor, which is singular. The minute, this is of course the electron microscopy of the 1T polytype we made in the lab. The 1T polytype exists in octahedral geometry, while 2H polytype is a trigonal prismatic. And as soon as we make it, look at the amount of hydrogen that we start getting. So it was really unbelievable, this result. Now, this is just completed. Ordinary MOS2 with 100-watt halogen lamp, very small amount of hydrogen comes out, very low turnover factor. You do with graphene, slight improvement. With nitrogenated graphene, not bad, slight improvement. However, when you heavily nitrogenated graphene, the one we did, we got very large amount of nitrogen. But you don't need to do that. You just take the new polytype of molybdenum sulfide, we get with even with a 100-watt lamp, we get enormous amount of hydrogen. This is worth exploring. If this is true, in fact, we have found high cyclability and stability for hydrogen production in this. Of course, I have to make a huge scale to show people. In fact, recently my friends in Berkeley had a BBC and CNN had a show, they're showing how they are producing hydrogen and save mankind eventually through that. I want to make a similar one with these things and show how much hydrogen I can produce. But it's really fantastic, these materials. Knowledge of solid state chemistry is very, very important, chemistry of materials, because if I did not know about this unusual polytype of 1TMOS2, I wouldn't have even done this work. I'm telling you, why am I telling you this? All this is over 2 months old. This is yet to publish in Angamanta this month, or next month, and not this month, next month. Well, the reason is in the last 3-4 months, suddenly the world suddenly has become conscious of 1TMOS2. Wherever you go to any conference, people are talking about MOS2 as being a futuristic material. They are thinking of all kinds of properties. People are producing, theoretically predicting all kinds of properties, producing all kinds of new results. For example, what is one of the new results? Well, people are predicting unusual kind of dielectric properties of 1TMOS2. And there are people who work on topological material, topological insulators. They are saying 1TMOS2 surface is a topological insulator. Well, I don't know whether it's true or not. There is sudden excitement. And so if I were to work on one exciting material today, I would say MOS2 is certainly one of the most exciting materials. So this is something I want to tell you, how MOS2, which I have been working on, has become so interesting. Well, we have done many other inorganic materials. Gallium sulfide, gallium selenide is also just like graphene. We have made transistors out of that. You can see that blue, that chip, there is a single layer gallium sulfide, single layer gallium selenide. We can measure the thickness of these things. You can study the Raman spectroscopy. All these we see as a bunch of layers. What happens to Raman spectroscopy, how one Raman mode stiffens, another mode softens, and so on in these materials. We have done all that with gallium sulfide. Then we have made transistors out of gallium sulfide and gallium selenide and studied the transistor properties of these materials as well. And now we have also looked at materials like niobium selenide, single layer, and looked at superconductivity. As you know, niobium selenide is a well-known layered superconductor, and you can see bulk material superconducts at 8.5, single layer is around 3.5. This is a picture of a single layer niobium selenide. So we are yet to work, this work is not complete. We are yet to do much more on these materials. Okay, I'll get rid of all this sulfide, selenide, all this time. We do something completely different. One of the most well-known materials, which is a layered material, is boron nitride. Some years ago, 2-3 years ago, we made a very nice boron nitride by a simple high temperature reaction. A lot of people use this method. A single layer boron nitride, one sheet, you can see the thickness is only 0.4 nanometers. We could make boron nitride of various forms. You can see these pictures. These are one layer of boron nitride, just like graphene. You can even measure right, with a foot rule, ordinary scale, you can measure the distances here, 1.44 angstroms with boron nitrogen length. These are few layer boron nitride. There are many layers here. They can make single layer, few layer, and so on. And now magnetism also of these materials we have studied and show they are also magnetic, single layer being most magnetic. Very interesting is many people use boron nitride to make strengthening of composites, and what we try to show is if you put a single layer or 2-layer boron nitride, it is a much better material to make composites than ordinary boron nitride. People dump a lot of boron nitride into polymers. It is not the way to do it. What you have to do is make single layer or 2-layer, put a small amount of it, and that is enough. And the smaller the number of layers, better it is for strengthening composites. So these are all some of the things on boron nitride. 1 minute on this material. You see, one of the responsibilities of good material scientists, or at least chemists like me, is not only study materials which are known in new forms, study new properties, new phenomena. That is one aspect. Other is create completely new materials which are not known to man, not known to chemistry. One of these in our lab has been making borocarbonitrides, BcN. Boron and nitrogen are either side of the carbon in the periodic table. But can we make borocarbonitride? In fact, one of our methods is by using reaction of activated carbon with boric acid and urea at high temperatures. You can also do by gas phase reaction. The gas phase reaction gives very low surface area material. By this solid state route of ours gives you high surface area material. I will not bother you with the details of characterization, how it has boron, carbon, nitrogen, as studied by X-ray photoemission and other means. The trouble with these borocarbonitrides is it can have rings of boron, carbon, nitrogen, but it can also have sort of domains of carbon with domains of boron nitride. Both are possible, but most of the materials we have seem to have these extended structures of these rings, which is very nice. It is not completely homogeneous. Sort of a composite is a combination of properties, but unusual properties. I'll tell you what I mean by unusual properties. The borocarbonitride, some of them we have made, has very, very large surface area, 2,000 square meters per gram, or 1,600 square meters per gram, very, very large surface area. They also absorb CO2, and you see carbon dioxide, 65% carbon dioxide at room temperature. You see, this is the kind of thing we have to do. You see, what unfortunately chemists are doing and material scientists, they are working on fancy materials like metal organic framers. I also do a lot of work on that. They are showing that, oh, it's very good for hydrogen, very good for CO2, but each gram costs $20. You can never use that material for real practical application. Anything you will use in engineering and technology will have to be inexpensive. So this is the cheap material, borocarbonitride. This, I think, will have some future because both carbon dioxide and methane is quite good. And there is also good selectivity. Selectivity for CO2 over nitrogen is about 10. Which is not bad. CO2 is here, nitrogen is here. Not too bad selectivity. So this is one thing, gas adsorption property of a completely new material. Well, I'm not going to talk much more, but what we have tried to show here is by theoretical calculations where exactly these molecules bind in borocarbonitrides, the binding sites for CO2 and methane and hydrogen we worked out. Well, again, 1 minute I'll take off. I'll not bother you with the frames here on the screen. In the last 1 month, 2 months, this work is all only 2 years old. People have found borocarbonitrides are the best means of making oxygen reduction. I hope you know oxygen reduction reaction, ORR, is a very important thing for technology, for energy area, oxygen reduction. More than that, just now, this month, borocarbonitrides have been shown to be probably some of the best material ever found for lithium battery applications. It is not my work, but I feel very proud that, of course, I sent the samples to these people who make these lithium battery research, a lot of them, and all of them have uniformly found these are outstanding materials. So something that purely started as an academic interest for me, molybdenum sulfide and so on, has become one of great interest. Borocarbonitrides, just to make something new, we started doing it. Now they are finding enormous applications for some of these things. These are supercapacitor applications, but I will not talk about that today. Okay, I'm coming to a close, but describing a number of things. Why am I talking about this seminar here in this university? Well, anything you start, does it have a future? In fact, does anything have a future? Well, the amazing thing is these layered materials, there are so many in the history of chemistry. If you go through, people have described everything. And is it possible to make layered structures of all kinds? For example, this oxide, very well-known oxide. So MoO3 is a layered oxide. Can I remove one layer out? Well, we have done that. We are able to remove one layer out. Not only that, we have studied, look at the electronic spectrum. The single layer MoO3 has a nice blue shift compared to bulk MoO3. We have studied a number of properties of these materials. These are all very complex oxides. You see, I can take one layer off, and see the thickness of this is all one layer or two layers, and we can study materials of this kind. Just the last couple of weeks, one of my students has taken layered ferroelectrics and removed one layer of that layered ferroelectrics and studied properties of this kind. So new layered oxides, single layer, two layer oxides, may have many applications. I do not know. They are worth studying. Similarly, lot of molybdenum, just like molybdenum sulfide, we have got metal organic frameworks, a lot of work going on probably even in Waterloo. Lots of inorganic chemists work on metal organic frameworks. Many of them have layered. I can remove one layer or two layers by either exfoliation, ultrasonication. And you see here is a material which you have grown. A bulk is giving a luminescence band here. As soon as you make one layer or a two layer, you see it shifts. A lot of properties of this kind have yet to be studied. And towards the end, the last few frames, what I will show is graphene is so wonderful. Can I make graphene itself as a base for making new kinds of framework structures? Well, this is something we have done. For example, you take graphene, around that you make a metal organic framework of lithium benzene dicarboxylate, for example. And you can see how this is the lithium benzene dicarboxylate, a metal organic framework. I put it in graphene because these are the graphene Raman bands. These bands are also there. Raman bands are the metal organic framework. Such composites have very interesting properties. For example, the lithium ion conductivity in these graphene composites with the lithium metal organic framework is much lower. The activation energy comes down. And this kind of study we are conducting. We are also looking at optical properties, ligand sensitized lanthanide emission. In the case of bismuth compounds, these are all materials, gives wonderful colors with different rare earths. I can make graphene composites with these things, and you can make materials with all kinds of morphology. I will not bother about. You can see what happens is the wonderful photo emission we had in the original rare earth doped material. As you go on putting graphene, of course, the material quenches that, because this may have a ability to do tuning of the photo emission and tuning of the lifetime of the and quantum yield using graphene composites. So this is one thing we have. This is not yet published. This is something we have done. One thing we have published just now recently is a composite with a very well-known metal organic framework. Everybody knows ZIF-8 is a very well-known material. Everybody works on that. It is the imidazolate metal organic framework. This is graphene. Grow that imidazolate on the graphene and make a composite out of that. And you can see it has wonderful surface area properties, surface area varying with the graphene content. But what is interesting is it also has very interesting carbon dioxide absorption. Lastly, this is something I am very proud of, not yet published, just sent to a journal. You take a layer of graphene and couple with the Shinogoshira, one of these coupling reactions, make one layer coupled with different linkers. I can vary the length of the linkers, and now I can make an all-carbon porous material wherein I have linked graphene by different linkers of different lengths, linkers of different lengths, and it gives you a completely new type of all-carbon porous material. All carbon porous, no metal, nothing. So you can see this has very high surface area. I've just given you typical result, 800 square meters per gram. It also has very good carbon dioxide and other adsorptive properties, which I will not bother you about. This is just to show the absorption of H2 hydrogen and carbon dioxide in all carbon material, purely carbon-based porous materials which we have prepared. So these are all some of the things I thought I would talk about today in presenting you an entire world that has opened to me working on these layered materials, which are other than graphene. So I think there are many more things we can do. In fact, right now in my laboratory, not only are we making new materials, others have taken up. That is a nice thing, you see, being in my academic profession. You create an area, it develops into a big thing, leave it to others to work. And so you create another area. So that is where it is very exciting. Because I don't want to, there are people who put a bullet in a dead horse. I don't want to do that. In research, I think you leave the others to put the bullet, and I will do other things. So what this area has given me is an enormous excitement in the last 3-4 years of creating not only new materials, which are like graphene, new phenomena, new properties like hydrogen production, new gel electronic properties, new kinds of transistors, and so on. It has been a wonderful excursion indeed. I hope that if I ever give a talk again in Waterloo next year, I will talk about hydrogen production, where we have had very major results, which I have not talked about today, and also artificial photosynthesis using some of these very interesting inorganic material. These are some of my students who have contributed to my research. Actually, there is a statue of Buddha there, and this boy is blocking head of Buddha. But anyway, it doesn't matter. So thank you so much.
Questions for
Yeah. No questions? Yeah.
Single question in the HRTM images.
Yeah.
How could you see those patterns very clearly?
Oh, that, what we do is ordinary microscopes like the one you have just bought here, it won't give you such P measure. You will have to use an aberration-free microscope, and that is how, where you maintain the temperature, everything so precisely around the thermal microscope, and because it's aberration-free, you can measure distances of the order of half an angstrom or something very nicely, or 1 angstrom. Otherwise, ordinary microscope do not measure. You're right, but this is an aberration-free Titan microscope. That's how we could measure. We could photograph like that.
You have this facility in IISc?
This is my Nehru Center, Jawaharlal Nehru Center. It is a $7.5 million microscope.
Can you talk about the mechanism of hydrogen production from the moly to sulfide?
Yeah. Well, yeah, actually, molybdenum sulfide actually comes in the end. It gets the electrons from the graphene normally, and the protons are produced by some other method. Water is decomposed because you produce another material, you excite, you get the electrons and holes go away somewhere, and I didn't talk about that. We use another method to get rid of the holes, and the electrons eventually come to the graphene, and that electron is transferred to molybdenum sulfide, and molybdenum sulfide reduces the protons. That's what happens. But I can actually, I wish I had given the talk on that to show you the energy level diagram. This is what is called a Z photosynthesis. It is called the Z mechanism of in photosynthesis. We have an analog, semiconductor analog of photosynthesis. Everything that happens in a photosystem, it do the same thing. They excite the electron, get holes and electrons. And what happens in a plant is that the electron eventually gets annihilated by a hole in photosystem 1, and it again creates electron by excitation, and that goes to reduction of proton. And the same thing I do here, except that I'm using all semiconductors. Molybdenum sulfide is only used for reduction of protons in the end. And suppose I use, it depends on what semiconductor you use. Otherwise, sometimes what you use a dye sensitization. In this case, I've done that, in which case you use a dye, and the dye absorbs the first photon, gives out an electron, and that electron goes to graphene, and that eventually goes to molybdenum sulfide. And the hole, normally what we do is use a scavenger to remove the hole. Usually you remove the hole by various ways. Some people do a chemistry, put a sulfide or thiosulfide or sulfide which gets oxidized in some way using the holes. Or I use organics. I use something like benzyl alcohol, and it becomes benzaldehyde using the holes. So we have to scavenge the holes and use the electrons. Here I've only used the electrons to reduce protons. The other one I talked about, which I told you I just published in PNAs, I only use the oxygen there to produce splitting of water. We do both. You need both in photosynthesis, production oxygen and hydrogen. This is only for hydrogen.
In terms of synthesis, you can vary the stoichiometry from graphene through to boron nitride.
Well, that will be a mixture. It form a compound.
Yeah, okay.
You see, the trouble is you can make composites of boron nitride and graphene. We do that. Many others do. A lot of work going on in Rice University on that. I also do that. That will be different. See, what we have tried to do is, if possible, as many links as possible with borocarbonitride, boron carbon nitrogen rings. So what I essentially get here is borocarbonitride rings with small domains here and there of boron nitride. Maybe it's a little bit of graphene. You can never determine the structure by crystallography because there will be a single crystal. But you can see by XPS and other methods that you have formed boron carbon bonds and boron nitrogen bonds. We know there are there. But it is not a pure compound. But you see, that is the thing. The future of the world will not be based on pure compound. It will be based on interesting composites. And this is a composite. BCN is a composite.
So yeah. Are there any advantages to using lead boron nitride compared to lead graphene?
Boron nitride alone is an insulator. It's not very useful for anything. But borocarbonitride, carbon is too conducting. See, that's why we want to make it a bit less conducting, have a gap. When I do borocarbonitride, there is always a gap. More than that, it creates highly localized dipoles. Those dipoles are very important for adsorption of CO2. The theoreticians have done a lot of calculations about how they bind to some of these dipoles. They're very interesting electronic properties, which I didn't talk about, which we have also studied in the case of borocarbonitrides. And that is one reason it becomes a very good electrode material. The mere boron nitride will be useless as electrode material. Carbon, of course, we know how it performs, very conducting. We want something in between. And therefore, what you should have asked is, what about the composition control? That is the problem. How do you know the composition of borocarbonitride? So with a lot of effort last 1 year now, I can make BCN, BC2N, or just BCN, BC5N. BC5N is the best, enough carbon to make it conducting, but the boron nitride to make it not so conducting. So you have to fool around with composition as well.
Okay, any other questions? If not, please join me in thanking Professor Rao for
okay, thank you.
exciting lecture.
Thank you. Thank you.